So I'm going to switch to my browser. And you said it was question 6, is that right?
Mm-hmm.
Oh, I'm in the wrong section. Okay. So for that one, you're supposed to calculate the energy of one electron or one microwave.
Mm-hmm.
And then you're supposed to calculate the energy that the eye absorbs.
Mm-hmm.
And then do you remember that idea of the energy of one times the number of photons is equal to the energy total?
Kind of.
We talked about that with problem number 2.
Okay.
It's the same thing.
So what did I do for that one?
Well, let's take a look at the solutions. So that way I can tell you and show you at the same time, rather than tell you and make you look up at the sky. Okay, so if you take a look at number 2 here, do you see that in the middle of my browser here, it says that, oh, I'm showing you, I was looking at number 1. Oh, number 2, I'm sorry, number 2 is not like that. Number 3, my apologies, how many photons?
Okay.
So if you take a look at that line there, and it's unfortunate that it's written this way, but then I wrote down, since the number of photons times the energy of one photon is equal to the total energy,
Uh-huh.
or n times E sub 1 is equal to E total, right?
Yeah.
So that means when you solve that equation for n, you get E total divided by E1.
So yeah, what I did was the energy of the signal divided by the energy of the wavelength, which I calculated.
And I got 8.3 times 10 to the 25 photons. What did you get?
Not that. Oh, for number 6. Well, I don't know. I didn't do anything else.
Oh, okay.
So
For
for
number
this
2,
one,
let's go back to number 3. What did you get for number 3?
5.9 times 10 to the 4th.
I got times 10 to the 5th. What did you get for the energy of one photon?
4.226 times 10 to the 19. But
Negative
I have,
19, right?
yeah, with 2 sig figs. Right?
Right. I have too many zig figs on my answer. I see that now, but
Okay.
Nonetheless.
And then I have that correct, 2.5 times 10 to the negative 14 joules divided by 4.2 times 10 to the negative 19 joules gave me 10 to the 4th.
Oh, it should, I'm looking at this and it should be 10 to the 4th. I'm not sure what I did wrong with my calculation. So it should be 5.9 times 10 to the 4th.
Got it.
I'm going to
So
go ahead.
you're telling me I was right and you weren't?
Yeah.
Okay,
What's wrong with that?
nothing, just making sure I heard that correctly.
If
So
you want
number,
me to, if you want me to be perfect, you're making a big mistake
uh-uh.
because I may act like I'm perfect, but I'm not.
So number 6, I would do the same thing. I just was getting thrown off with there being a Q in there when it's the same thing.
Right. Only, yeah, see, this time you're being asked to calculate the energy, right?
Mhm. Yeah, so I got Q.
So that's what makes it different.
Okay. So I would divide the two values I calculated to get the number of photons.
What did you get for those two values? I got 130 joules.
I got 132 joules.
Okay. And that's correct. But when you round down, it becomes 130.
Because it's only 2 sig figs. Okay.
Yeah. All of those numbers only have two zig figs, the 4.0, the 11, and the 3.0. And then what did you get for the other value?
I got 1.65 times 10 to the negative 28.
I got negative 24.
Oh, I see. I have my
Well,
denominator different than you.
so did you use 12 times 10 to the minus 9 meters?
I know. I see what I did.
Is that what you did?
No, I calculated centimeters to meters and then to nanometers when I didn't need to put it into nanometers.
Oh,
I should have just stopped at meters.
right. So the big picture item there, Charlotte, is that when you are getting rid of a prefix, you put down the number that it represents, and that's good for any prefix, whether it's nano or centi or kilo or whatever.
Right. So they do
You just
this.
have to remember what number represents what prefix. And
Yeah.
actually, it should be said the other way around. You should know what prefix actually means what number.
Right. So then, okay. So
Now, if you got 10 to the minus 28, I have the feeling that you actually didn't use, I'm betting that you didn't use your denominator correctly. What did you have in your denominator there? Did you have 12 times 10 to the minus 2 meters?
I have 1.2 times 10 to the 12 times 10 to the negative 9 meters.
Yeah, that's fine.
Oh,
What?
okay.
That's almost fine. Almost fine. It's actually 10 to the 12 times 10 to the minus 9 is 10 to the 3, right?
Mm-hmm.
And it should be 10 to the minus 3 if you're going to do 12
Yeah.
or 1.2.
Yeah.
Actually, if you're going to do 1.2, it should be times 10 to the minus 1. So I'm not sure how you converted that, but you really need to be careful about how you convert things. And that's why we write out the conversions rather than just kind of think about it and and come up with a number. Like I highly recommend we do not just move decimals over and things like that because there's too much room for error.
Right.
And you know, I think I'm pretty good at working with that kind of stuff, but whenever that happens, I always make errors, you know, at least 1 out of 10 times. And that's one time too many.
Yeah. So
And
then,
yeah, and I was going to say, I sometimes do it, you know, 2 or 3 out of 10 times, and all of a sudden you're looking at a C if they don't give you any partial credit. So you can see that everything that I've done here, I've pretty much shown how to do the calculation, how to do the conversion, or I will substitute when appropriate.
Okay. That was the only one that really gave me trouble, so
Okay,
I'll work on it again.
so do you want
Um,
to, it's time to start some chapter 7 stuff. You looked at any of the videos?
Yeah, I'm almost done with them. I do have a question about screening and penetration.
Okay, about screening and penetration? Sure.
Yeah, I was listening to you explain it in the video and yeah, it just wasn't.
Well, it's not going to get it any better here because it's a tough subject. So let me do a new share here, but we'll give it a go, okay? Okay, so what we're really talking about is something called the effective nuclear charge.
Mhm.
And it's called Z star. And this is the charge that really determines the energy of the electron. And when I say energy, I'm talking about the stability of an electron. And basically, the higher Z star, more stable. Okay? So this is going to look like a Bohr's atom, but it's really supposed to be a Schrodinger's atom. And I don't want to try and draw spheres, okay? So here's the n equal 1 shell. And here's the n equal 2 shell, and so forth and so on, okay?
Mhm.
And like I said, it's going to look like Bohr's atom, but I don't want to try to draw spheres. Now, you can have 2 electrons here in the first shell, and that's the maximum you can have in the first shell. And then you can have an electron in the second shell. Now, what is the region of space you'll find these n equal 1 electrons? Usually somewhere in this region here, between the nucleus and the edge of the shell. That's your 90% boundary. Now, where are you going to find this second electron? You're going to find it between here and here, and that's your 90% boundary. So what you're supposed to think here is that this electron that's in the second shell can actually be closer to the nucleus and more stable than these electrons in the first shell for some given amount of time. So here, this electron is being shielded from the nucleus by the n equal 1 electrons. That is if the electron's way out there.
Is that the same term as screening in this case?
Yeah, screening and shielding is the same thing. I call it shielding, screening, screened. Okay, now suppose this is the case. So we know that this electron can actually be pretty close to the nucleus, correct?
Mhm.
So here, this electron penetrates the screening. Screen is probably a football term where a screen is when you protect things. Now, here, let's talk about the electron here. The n equal 2 electron experiences a Z star, and here we're going to make this nucleus a 3+ nucleus, experience a Z effective of about +1. So why does this electron, when it looks at the nucleus, see a +1 charge? And the answer is, do you remember how charges are additive?
Mm-hmm.
This electron can't really see these two electrons, and it can't really see the nucleus. They're far too small for it to see, as it were. And they're too far away to see, to feel individually. So what it does is it takes all of this and adds it up together. So what's a -1, a -1, and a +3 equal?
+1.
So that's what it experiences. What about this electron? The n = 2 electron experiences a Z star of +3, because there's nothing in between it and the nucleus. So when it looks at the nucleus, it sees a +3. Okay. So that's what's happening with these outer electrons compared to the inner electrons. Now, furthermore, this electron that's out here in the second shell, it's a +1 sometimes for the Z star. It's a +3 sometimes for Z star. Where does that electron spend most of its time? Does it spend most of its time being screened or penetrating the screening? Now, do you remember the little chart we drew before for the probability? This is a 1s.
Mm-hmm. Oh,
and this
yeah.
is a 2s.
Yeah.
So where does that electron spend most of its time? With a +1 or a +3?
+1.
A +1. So here the average Z star will be closer to +1. Okay, so that's a start, but we have to finish it off. Are you ready?
Sure.
Okay. So here, this is why NS is more stable than NP, is more stable than ND, is more stable than NF. So here, if we go to the fourth shell where we have all of these, a 4s is more stable than a 4p, is more stable than a 4d, is more stable than a 4f. So here we're talking stability. When we look at second shell, it's going to be 2s is more stable than a 2p. There's no such thing as a 2d, so we don't have to include that. Okay, so when you look at these curves here, and what I'm going to do here is I'm going to do a new share. And I'm going to type in NS versus 2P probability. And hopefully I can get the images that I'm looking for. Okay, so can you take a look here at the 2S versus the 2P?
Yeah.
Can you see that the 2S has that little hump at the near the origin, but the 2P does not?
Right.
So that means that the 2S penetrates better. So that means it's going to see a +3 better than a 2P, okay?
Okay.
So on average, if we look at this, so here's my 2S, and 2S. And let's see, I'm trying to kind of draw this true to form. Here's a the 2p, and then the 1s. Oh, I should have used the purple for the 1s to make it look like this guy. Here's the 1s. So here, with this little hump, the 2s penetrates better. So Z star is greater. And if Z star is greater, that means that 2s is more stable. And all of this compared to what? Then 2p. So this would be the same case if you did a 4s, a 4p, a 4d, and a 4f. If we plotted these, we would find that the 4s penetrates better than the 4p, 4d, and 4f.
Okay.
And what would happen, the only difference between these drawings would be that, you see how the 2p has one hump here?
Mm-hmm.
The 4s, or the 2s has one hump, I'm sorry. The 2s has one hump. The 4s would have three humps. The 4p would have two humps. The 4d would have one hump, and the 4f would have no humps. The more humps you have, that means the more likely you are to have some electrons near the nucleus. And this is what I mean by the little hump here.
I can only
wait,
see you.
you can't see what I'm talking about. I'm sorry. I think that you can see what I can see. So you see this 2s here with the one hump and then the second hump?
Yeah.
If we did this for the 4s, 4p, 4d, and 4f, it would probably look something like this, where this would be that would probably be the 4s, something like that.
Okay.
And then the 4p would probably look something like this. (4p). Let me see if I have any other colors here. I have green. And the 4d would probably look something like this. (4d). And the 4f would look like this. So the more humps you have, the more likely you are to be close to the nucleus, and therefore an electron in that subshell will be more stable. So why do more humps matter? Because the electron penetrates the screening better.
Okay.
So that's what it's all about. And the name of the game is ultimately this. Z star, which is the effective nuclear charge, determines the stability of the electron. The higher the Z star, the more stable. Now I want to show you one more thing here that's pretty important. Not for you to memorize, but rather so you can see Z star. Now remember, we're comparing Z star for electrons that are in the same shell, right?
I guess. Yeah.
We are. So here is the table of some effective nuclear charges. So you'll notice that for lithium, so this is for a 2s in the second column and a 2p in the third column. They don't really have a Z star for lithium because there is no electron in the 2p subshell, okay?
Right.
But for boron, boron has 5 electrons. So with 5 electrons, you would expect it to have a nuclear charge of +5 because it's got 5 protons in the nucleus, right?
Mm-hmm.
However, 2 electrons are in the first shell, and they're going to screen, so that's going to drop the effective nuclear charge to a +3, right?
Yeah.
But you also have 3 electrons in the second shell, and those electrons can screen other electrons in the second shell.
Right.
further reducing the effective nuclear charge. And so here the 2s electrons penetrate that overall screening a little bit better. So that's why you get a 258. The 2p penetrate the screening less well. That's why you get a 2.42. So the 2s are more stable than the 2p. And the important thing here is not the numbers, but to look at which number is bigger in each case. Do you see 322, 314?
Mhm.
The 2s electron is more stable. 385, 383, the 2s electron is more stable. 449, 445, the 2s electron is more stable. So without any sort of glitch or hiccup, the 2s electron is always more stable than the 2p electron.
Can we draw one? Can we draw boron?
No, it's really okay. Okay, you asked for it.
I mean, you did.
So here's
list
boron with its
electrons.
5 protons, and on average, it's 6 neutrons, okay? Now, I have to zoom out so that you can see what I'm drawing. So here's the n equal 1 shell, and here's 2 electrons, right?
Yeah.
And here's the n equal 3 or 2 shell,
Mhm.
and there's 3 electrons. Okay?
Mhm.
Why does the focus on that look so bad? Yeah, that's better. Okay, so here, let's call these 2s electrons, and let's call this one a 2p electron. Okay?
Right.
Now, which of these electrons on average is closer to the nucleus? The 2s or the 2p?
2s.
Right. This is closer because better penetration, right?
Yeah.
This is farther because it's less penetration.
Okay.
Okay, so we're just going to look at one of these 2s electrons, just one of them. And I'm going to draw that down here for the 2s. So here's my nucleus. Here's my n equal 1 with 2 electrons. And here's a 2s, and here's a 2p. So this guy, the other 2s, can be down here. It can be over here. So this is the 2s. But on average, it's going to be closer than the, well, it's hard to draw, but I'm, giving it a shot. You did ask for it. So what I'm going to do here is I'm going to make this a large E. And because this 2s electron spends more time closer to the nucleus than this situation over here, where this is a 2s and this is a 2s. And this is the 2p. Notice here I made the electron a little larger, farther away from the nucleus. So here, Z star is going to be greater. And here, Z star will be smaller. Simply because the 2s can penetrate better than the 2p. And the size of the electron tells you how well it penetrates, okay?
Okay.
So, it's very conceptual. You have to be able to have a great imagination of what these electrons are doing. All right.
All right.
And I'm willing to bet that this little drawing didn't help you one bit.
A little.
So again, the reason this 2p has a smaller effective nuclear charge is because it's not getting as close to the nucleus as the 2s is.
Right.
Okay, so here, this guy's experiencing a +5, right?
Which
This
guy?
guy is experiencing a +2, but also these guys are going to be closer to the nucleus sometimes too. I mean, it's a really complicated picture
Yeah.
because nothing says that these electrons have to be on the border, right?
Right.
So where are they going to be? They're going to be somewhere in here also.
In between.
So they're kind of like jockeying for position and, trying to get inside the screening. And who's going to be able to get inside the screening first, the 2s or the 2p? Well, the 2s, because its probability is greater closer to the nucleus because that little extra hump it has at the beginning.
Okay.
Okay, so that's effective nuclear charge. And you understand how to get electron configurations?
Yeah.
Okay, so here's the best way to get electron configurations. So this is the first period, second, third, fourth, fifth, sixth, and seventh. Okay, so you want to, this is the block method, SPDF block method. And what you want to do is, remember, this is the 1s, 2s, 3s, 4s, 5s, 6s, 7s. This is part of the 1s, but it's written over here on the right. This is the 2p, 3p, 4p, 5p, 6p, 7p. This is the 3D, 4D, 5D, 6D. Now here's where people always make a mistake. You see how this is the fourth period, but this is 3D?
Yeah.
I mean, this matches, right? 4S4, 4P4,
Yeah.
4, 3D. Oops. Well, tough luck. You have to remember that's 3D. And this is 4F and 5F. And remember, 4F really starts right here. This is where 4F starts, right there, which is in 6. So I'm going to come back to this in just a moment. The way I kind of remember it is if you look at the blocks, this one starts with 1S, 2P, 3D, 4F. 1, 2, 3, 4. SPDF.
Right.
Okay. Which of course does nothing but confuse us when we start thinking about quantum numbers and knowing that S is 0, P is 1, D is 2, and F is 3. But that's different. So just remember, each block starts with 1S, then 2P, then 3D, then 4F. Okay, so if you remember that, you can get the electron configuration. You can predict the electron configuration of any atom. You'll get about 80% of them correct. 90% of, or the other 20%, you'll get about 80% correct. It won't be perfectly correct, but it'll be like 80 or even 90% correct.
Right.
So it's a great model for predicting the electron configuration of atoms. All right. So here's our model. Here's the new model. And I'm going to go ahead and do this. Okay, so if we want to get the electron configuration here of hydrogen, it's going to be 1s1. So hydrogen is in the S block, and it's the first element in the S block, so that's what this 1 is here. If we look at helium, remember this is part of the 1s. Helium is also going to be 1s, but it's 1, 2. It's the second element in the 1s, so 1s2. So what does this mean? This means n equal 1. It's an S subshell. And there's 1 electron. This is n equal 1. S subshell. 2 electrons. Now, what would lithium be? So here's lithium. And remember, this is 2s. So for lithium, you start here at the beginning and you go 1, 2. You have to go through the 1s. 1, 2, you have to go 2 elements through it. And that basically means your electrons are in the 1s, and there's 2 of them. And then you hit the 2s. And how many elements do you go into the 2s block? You go 1 time. So those are your 3 lithium electrons. Okay, so now let's do something really complicated, okay? So students should have seen this in their previous chemistry class. And a lot of times in their previous chemistry classes, they just stop right there. They want people to be able to do anything up until, say, lanthanum, and that's it. But we're going to do hafnium. Notice hafnium is 72.
Yeah.
So when we read across for hafnium, so I got to grab my chart again. Here's hafnium. And it's 72. And right next to hafnium, we have lanthanum, which is 57.
Right.
So when we start reading across, this is the way we would look for hafnium. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 2, 3, 4, 5, 6, 7, 4p6, 5s2, 4d10, 5s2, 4d10, 5p6, 6s2, and then this lanthanum is going to be in 5d1. That's lanthanum.
Wait. Oh, okay, never mind.
3, 4, 5, 6, right?
Yeah, so we count how many it is into 5D.
Right, and so far it's 5d1, but we can see that hafnium is also going to be the second one, so we could say 5d2, right?
Yeah.
But what about
And then we go,
58, 59, 60, and all of those. 58 starts right here. Well, you have to go all the way here to get to hafnium. So you're going to have 4F14.
okay,
Okay, now this is not correct because once you read it from the periodic table, then you have to rearrange it. So here's my symbol for rearrange it.
yeah,
So to rearrange it, you do 1s2, 2s2, 2p6, 3s2, 3p6, 3d10. What have I just done?
the numerical order.
I put 3 before 4 because electrons in the third shell are more stable than those in the fourth shell.
Right.
So here, not only do we have to put the 4D in front of the 5s, we have to put the 4F in front of the 5s.
Oh, yeah.
So this is what it would look like. Furthermore, hafnium is number 72, right? When you add up all the electrons, so here 2 plus 2 plus 6 is 10, right?
Mhm.
2 plus 6 plus 10 plus 2 is 20.
Right.
Here you have 30, right? Because 10 plus 14 is 24 plus 6 is 30.
Mhm.
And here you have, oh, here you have 10, and then you have 2 more here. When you add these all up together, we get 10 plus 20 is 30, plus 30 is 60, plus 10 is 70, plus 2 is 72, which is the number for hafnium.
Yep.
So this is what we expect you to be able to do in this class, is be able to get the electron configuration of any element. So furthermore, there are other ways of writing this. So this is the SPDF method. So I'm going to write this out again. Hafnium, SPDF, 1s2, 2s2, 2p6, 3s2, 3d or 3p6, 3d10, 4s2, 4d10, 4f4. Oh, I'm going too fast. I'm missing things. So hafnium, here's the SPDF method. 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d10, 4f14, 5s2, 5p6, 5d2, I believe, and then 6s2. Okay, now, do you see where hafnium is right here?
Yeah.
Right here, this is in the period before hafnium shows up. Hafnium shows up in the 6th period.
So
Well, in the
xenon.
5th period, this is xenon.
Mhm.
So we can actually write the noble gas configuration. And the noble gas would be xenon.
Mhm.
So we actually start at xenon, and then we go here, 6s2, and then you can see we've got 5d2, right?
Yeah.
And then 4f14 for the ones below. Now, what does this symbol represent?
Rearrange.
Okay, so we're going to write xenon, 4f14, 5d2, 6s2. So this is called the noble gas configuration.
Okay.
And to write the noble gas configuration, you start with a noble gas preceding the element in question.
Okay.
There's also something called the orbital box diagram. So I'm going to do an orbital box / noble gas. So here, what makes this a noble gas notation is that we have xenon here. You with me?
Yeah.
So here, the 4F has 7 orbitals. If you remember, F stands for 3. 3 means -1, -2, -3, 0, +1, +2, +3 for 7 orbitals.
Yeah.
So here's my 7 orbitals. These 14 represent electrons, and you put them into these orbitals like this.
Hund's rule.
Yeah, we are going to follow Hund's rule. So I put the first 7 in with arrows going up. That's spin up or +1/2, right?
Yeah.
Then I put the second ones into each orbital, spin down. And that's the Pauli exclusion principle that says no two electrons can have the same set of quantum numbers.
Yeah.
So here, if we just look at one of these guys here, it's going to be N equal 4, L equal, what is F again? 3. M sub L is equal to, let's go with a -3, okay? And M sub S is going to be +1/2 because it's arrow up.
Yeah.
Now, what are we going to do for the 5D? How many boxes do we have in a 5D?
5.
Okay, because D stands for 2, right?
Yeah.
So how many electrons do we put in here?
Just 2.
And they both go in different boxes, spin up.
Yeah.
How many boxes for a 6S?
1.
1, because it's an S. And 1 up, 1 down.
Yeah.
So that's your orbital box / noble gas notation. Sometimes I do this way because I simply don't want to draw all the boxes.
Line. Okay.
Yeah, it's the orbital line notation.
And are you okay with either?
Yep, I am. As long as you make your lines so that they are separate from the other lines like these are. You can see the definite space here, right?
Right.
Don't crowd them all together. Just like here, you see how this set of boxes, we have a space between the next set of boxes?
Yeah.
Okay. Now you can actually use the box notation to talk about magnetism. If you have any single arrows, it's called what? Paramagnetic, right?
Paramagnetic.
But if you have all paired, then it's diamagnetic. Now, how do you know something's ferromagnetic? You can't tell by looking at the electron diagram. You can't. The only way to tell if something is ferromagnetic is that you put it next to a really big magnet. And if it becomes magnetized, it's ferromagnetic. So paramagnetic means it's attracted to a magnet. And diamagnetic means it's repelled. So that's a big part of this chapter is just being able to come up with electron configurations and understanding what all of this means.
Yeah.
So there is this atom that has the following electron configuration. So what element?
We have 29 electrons. Copper.
Yeah. Therefore, 29 protons, therefore copper. Now, what do we expect copper to be? Using the SPDF method.
Well, 4s1 before the 3d10.
Nope.
No. Okay.
1s2, 2s2, 2p6, 3s2, 3p6. Then what's after 3p6?
4s2.
4s2 and then?
3d9.
Right. And then we rearrange and what do we get?
1s2, 2s2, 2p6, 3s2, 3p6, 4s2,
3d9, 4s2.
3d9, 4s2.
That's what we expect. And here, they're not the same.
So what's with that? Why?
Well, it's pretty simple, actually. If you take a look at it, do you agree that this is where they're different?
Yeah.
Okay, so if you look at a 4s with 2 electrons in it and a 3D with 9 electrons in it, the way I'm going to draw the 3D is like a pie. So I'm going to draw a pie with 5 orbitals. 1, 2, 3, 4, 5, 6, 7, 8, 9. And my 4s, I'm just going to draw the electrons like this. So this is 3d9 4s2 versus four S2 or 4s1, I'm sorry, and 3d10. So 3d10, I'm going to draw my pi again. So these are the two situations we have. Are you with me?
Yeah.
Now, the name of the game is simply this. The better arrangement is going to be a combination of putting them into a more stable subshell and distributing the electrons better, because electrons repel one another.
Okay.
Right?
Mhm.
Okay. So in this situation, can you see that the electrons are evenly distributed? They say it's symmetrical. So here in this 3D, the electrons are as stable as they can possibly be because they're evenly spaced. And for the 4s, when you have 1 electron in there, it doesn't really matter. Now over here, you have 2 electrons in there, and it's pretty even to space those things in the 4s subshell.
Mhm.
Now look at this 3d9. Are these evenly spaced?
No.
No, you got this 1 electron that's got a whole bunch of room by itself, and all the other electrons are paired. It's almost like unfair, and there's a waste of space there. where you could put another electron in there and make it evenly spaced without much more effort, right?
Yeah.
So the two reasons why this is better is because a 3D electron is more stable than a 4s, correct?
Yeah.
But also, this arrangement is more symmetrical. And because it is more symmetrical, the electrons repel each other a little less, and it's better. So that's why. But it doesn't always work well in all cases. For instance, it doesn't happen for nickel.
Okay.
With nickel, you would have 3D8, and you'd have two spaces here, but it just doesn't work as well because you can't put those 4s's into the 3D. What other elements would be like copper and have this weirdness?
Silver
Yes. Why do you pick silver?
in the same group.
Yes. What else would be like copper?
Gold.
Why do you pick gold?
It's in the same group.
Because it's in the same group, so it should have a similar electron configuration. In fact, when you look at silver and we do the noble gas configuration, so what noble gas are we going to start with for silver?
Krypton.
Okay, so we're going to start with krypton. Then what comes next?
5s2.
Then what's next?
4d9.
4d9. That's what we expect, right?
Mm-hmm.
But it's actually going to be krypton 5s1 4d10. And then, of course, we have to rearrange this. And what would it be?
Krypton 4d10 5s1.
So you can see that that 4D subshell is full. It's very symmetrical, and so is the 5s. So this is more stable.
So do we do that with all of them that have this kind of property? Like,
Yeah, but you don't need to know which ones have this property.
okay.
What you need to be able to do is this. If I give you an electron configuration that comes up weird, you have to be able to figure out what element it is.
And it's weird because we have a larger shell with electrons in it when a smaller shell could have those electrons.
It's weird because it doesn't fit our model for predicting electron configurations.
Okay.
Okay. It's weird because it doesn't fit our model. So the SPDF model of predicting electron configurations does not work for all elements. But you can see for copper, even though it didn't work for it, 27 out of 29 electrons were correctly assigned, right?
Yeah.
And 27 out of 29 is like, oh gosh, I want to say over 90% correct.
Yeah.
Okay, so if I give you a weird electron configuration, you have to be able to tell me what element it is. Not only that, but you have to tell me what the electron configuration would be using the SPDF model.
Okay.
Okay. And ultimately, if I ask you for a reason, you're going to say, well, it's this way because the symmetry is better. And therefore, the distribution of electrons is better.
Okay.
So that's your basic argument, that the symmetry is better so that the distribution of electrons is better. And why do we want a nice distribution of electrons?
Because they repel each other?
Because they repel one another. So, you know, if you have this versus this, which is going to be better, left or right?
Right?
So this is better because you have a better distribution. And less repulsion. And this is worse because it has worse distribution and more repulsion.
So how do we evaluate the symmetry when given a electron configuration?
Well, that's just it. You don't have to.
Okay,
Again, you have to be able to pick the element if the electron configuration isn't what we expect,
okay,
and also be able to give the electron configuration for what we expect it to be. So on the exam, I'm going to ask you for electron configurations, and I'm going to ask you, okay, so what do we expect?
Okay.
So I may give you one where what you expect is not what you actually get.
right.
Okay. And that's a great way for me to test you because I can say, okay, what do you expect? And then I can give you the real configuration. I can ask you, so well, why are they different?
Okay.
And your answer is going to be, well, because the real one has a better distribution of electrons. It's more symmetrical, so it's more stable. Right?
Yeah.
Okay. So that's a good part of the chapter. The rest of the chapter is about periodic trends like what's the diameter or radius of the atoms in a period? What's the radius of the atoms in a group? What's the radius of ions in a period? What's the radius of ions in a group? What's the electron affinity of atoms in a period and atoms in a group? And what's the ionization energy of atoms in a period and a group? So we'll be looking at atom radius, ion radius, and we'll be looking at cations and anions because it's not fair to compare cations to anions, but it is fair to compare cations to cations. We're going to look at electron affinity. We're also going to look at ionization energy. We're also going to look at electron configurations of ions. And let me take a look at the table of contents. I think that's pretty much the whole chapter. It's not a long one.
Yeah. It is. Well, there were some chemical properties at the end.
The chemical properties are pretty straightforward.
Okay, I haven't gotten there yet.
They don't call it electron affinity. They call that electron attachment enthalpy.
Yeah.
And I guess the reason they call it electron attachment is because that's what you're doing is you're attaching an electron.
So that affects the bonding.
Actually, they're a little bit different.
Okay.
But as far as I'm concerned, we'll treat them the same.
Okay.
The deal is that when an electron attaches itself to an atom, energy is emitted and that's negative, right?
Yeah.
So the difference between electron affinity and electron attachment enthalpy is one of these is negative and the other one's just the absolute value of that negative.
Okay.
And the reason they do that is because in previous books, they would say stuff like, since the values are negative, they say, oh, this is less negative. And when you say less negative, it actually means larger. Like -1 is bigger than -2 because -1 is less negative, right?
Mhm.
So the way they were phrasing things, they would have to say, oh, it's less negative. And the way I phrase things is that the change in energy is smaller. Because we all know that energy can be positive or negative, and there really is no such thing as negative energy.
Yeah.
But we can say that the amount of energy change is smaller. So -2 is a smaller energy change than -5, right? Did I lose you?
No.
So -2 means like you've lost $2 from your wallet. -5 means you've lost $5. -2 is a smaller loss than -5, right?
Right. Yeah.
So that's the way to look at it's a smaller change, because change is either plus or minus, but there is no real positive change or negative change. It's just, did you lose or did you gain?
Yeah.
And let's see. We also did not discuss, but you mentioned Hund's rule
Mhm.
and the Pauli exclusion principle is what I mentioned. Do you remember what Hund's rule is?
Where you assign electrons one at a time per orbit per shell.
So you assign electrons to more stable
Mhm.
N
Mhm.
and also more stable NL first, and in orbitals, one per before pairing. For orbitals of the same energy. That's basically Hund's rule. And the Pauli exclusion principle is you can have no two electrons in an atom or ion have the same set of quantum numbers.
Right.
And it's because of this exclusion principle that we say that an orbital can only have 2 electrons in it. Because when you look at an orbital like this one, a 1s, and it's got 2 electrons in it, you've got N is 1, L is 0, M sub L is 0, and plus 1/2. And you've got 1, 0, 0, minus 1/2. And there aren't any other sets of quantum numbers you can have. So this orbital can only have 2 electrons in it. Right?
Yeah.
And if we look at a 2px, a 2py, and a 2pz, so here's your x, and here's your 2 electrons, here's your y, and here's your 2 electrons, and here's your z, and here's your 2 electrons. You can have 2, since it's p, it's 1, right?
Yeah.
And -1, plus 1/2, 2, 1, -1, minus 1/2. And here, you can have 2, 1, 0, plus 1/2, and 2, 1, 0, -1/2. I know my hand's in your way, but this one, what would be the sets of quantum numbers you would have for 2pz?
2, 1, positive 1, and then plus 1/2 and minus 1/2.
Excellent job. And so that's the tie into the previous chapter as far as that goes. So here you can see with the Pauli exclusion principle that you cannot have another one of these. You can't have that because you've already done that.
Yeah.
So Pauli excludes this one because it's not a unique set of quantum numbers. So you can see why it's called the Pauli exclusion principle. It excludes electrons from having the same set of numbers. Okay?
Okay.
So we did a pretty good job today, and we took it up a notch from what we learned in Chem 2, right?
Yeah.
And that's what we expect. So this chapter, there's not a whole lot of calculations. There's a whole lot of conceptualization. And so you really got to work hard to make this right in your brain, and then also be able to explain it and use it. I think it's in many ways more challenging than making calculations, or maybe I should say a different challenge.
Yeah.
Hey, thank you for calling in, Charlotte. I always appreciate it.
Okay. I'll see you tomorrow.
Okay.
Thanks.
Bye-bye.